Okay, for my first molecule, I have beryllium hydride, which has a molecular formula of BeH2. Beryllium has 2 valence electrons, and hydrogen has 1, and there's 2 of them, which means they're going to multiply by 2. So you have 4 valence electrons. Beryllium is our central atom. I'm going to write my hydrogens out here. Now, beryllium and hydrogen don't obey our octet rule, therefore this is our complete Lewis dot structure. As for the polarity arrows, they're going to be going towards hydrogen because hydrogen is more electronegative than beryllium. Okay, so for our formal charges, we have 0. They're all 0. They don't have a formal charge. So as you can see, overall, this is going to be a nonpolar molecule because the electronegativity is pulling equally outwards. Therefore, they cancel out. So this is nonpolar. And this is sp hybridized. As for my 3D model, what I used for my 3D model that I had around was marshmallows and toothpicks. I couldn't find wooden toothpicks, but I only had white ones, therefore it's kind of harder to see the bonds between them, but I tried my best to color them and to point them out. So my central atom right here is beryllium, and this is linear, therefore that's why it's straight. It's more straight than like angled off like this. So here I have my beryllium in the middle, and hydrogen's on the outside. Okay, so for my next molecule, I have methanol, or formaldehyde, which is CH2O. Carbon has 4 valence electrons, hydrogen has 1, and there is 2 of them. And then oxygen has 6 valence electrons. Therefore, this is going to equal 12 valence electrons. Carbon has is going to be the central atom. I'm going to write hydrogen down here, our 2 hydrogens, and then I'm going to write the oxygen on top. So once again, like in the previous molecule, hydrogen doesn't obey the octet rule, therefore it's just going to take a single bond on both of them. However, carbon needs to obey the octet rule, therefore if I just wrote 1, it wouldn't obey, and then oxygen needs this octet rule 2. So if I wrote 2 here, if I wrote another 2, it would still wouldn't work because carbon still needs 8. Therefore, I'm going to do a double bond here. And for polarity arrows, so hydrogen is less electronegative than carbon. Therefore, these arrows are going to point towards hydrogen is going to point towards carbon. However, oxygen is more electronegative than carbon. Therefore, carbon is going to be pointing towards oxygen. So they're all kind of pointing towards this way to the top. Therefore, that means that this molecule is overall polar. It's polar because they're all going towards 1. It has uneven electronegativity pool, and it is sp2 hybridized. So let me get my 3D model. So as you can see here, I have my carbon as my central atom, and I have my 2 hydrogens on the bottom, and here I have my oxygen on top. If you could see closely, I don't know how well you could see, but here I have 2 toothpicks to represent my double bond, as opposed to the single bonds right here. I had to put 2 double bonds to show that it's double bonded to oxygen. Okay. Oh, and the formal charges for this one, before I forget, are 0. Once again. Okay. So for my next molecule, I have silicon tetrahydride, which is SiH4, silicon and hydrogen. So silicon has 4 valence electrons, hydrogen has 1, there's 4, so this has a total of 8 valence electrons. Silicon is going to be our central atom again, or not again, but it's going to be our central atom. And then we have our 4 hydrogens, which is going to be a tetrahedral shape. Our polarity arrows. So hydrogen is more electronegative than silicon. Therefore, they're all going to go outwards, all these arrows. Okay. Wait, let me drop. For our formal charges, they're all going to be 0. Okay. This is going to be nonpolar because the electronegativity is pulling equally outwards. These are going outwards and these are going outwards. It's equally dispersed. And this is sp3 hybridized. Get my model here, my 3D model. So here I have my central atom of silicon. I have my 3 hydrogens on the bottom, and then I have my my last hydrogen on the top connected by a bond. Okay. For my next molecule, I have phosphorus pentafluoride, which has a molecular formula of PF5. Phosphorus has 5 valence electrons, and fluorine has 7, and there's 5 fluorines. Therefore, this is going to be a total of 40 valence electrons. Phosphorus is going to be our central atom, and there's going to be, we're going to write our 5 fluorines. I'm going to write 3 on the bottom and 2 on the top. Write our single bonds. And then we write the dots for this. Okay. For our electronegativity, or our polarity arrows, fluorine is more electronegative than phosphorus. Therefore, all these arrows are going to point outwards. Okay, and our formal charge is actually going to be 0 for all these. Okay. This is a nonpolar. They are equally dispersed. And it is sp3 hybridized. sp3d hybridized, sorry. Trigonal bipyramidal. And here I have my 3D model for this one. So since there's starting to be more atoms, I started to use smaller marshmallows because it would be too big and it would just fall off. So here I have my model here. I have my central, put them alongside. So I have my phosphorus like right here. I have my 3 fluorines on the bottom and I have 2 fluorines on the top. And there's my model. Okay. For my last octahedral molecule, I have silicon hexafluoride, and it's going to be hexafluoride ion, which is actually going to be a molecular formula of SiF6 2-. So silicon has 4 valence electrons. Fluorine has 7. There is 6. And the 2 minus is actually going to be, we're going to add 2. So this is going to be a total of 48 valence electrons. So silicon is going to be our central atom. I'm going to write 3 fluorines on the top and 3 fluorines on the bottom. I'm going to write out our dots for our octet to obey our octet rule. Okay, so that should obey our octet rule. However, this is going to be an ion of 2 minus, therefore you're going to write the brackets and then the 2 minus on the top right. For electronegativity, fluorine is more electronegative than silicon, therefore these arrows are going to point outwards. Okay. As for our formal charges, fluorine is going to have, all our fluorines are going to have 0 charge. However, our silicone is actually going to have a 2 minus charge. Okay, and this is actually going to be a polar bond, or a polar, overall a polar molecule, because as you can see, it's pretty uneven. It's going outwards, but it's uneven, therefore it's polar. And then it's going to be sp3d2 hybridized. Let me show you my model for this. So here I have my silicone as my central atom, the big marshmallow, and then 3 on the top and 3 on the bottom to represent my fluorines. Okay.